Other IR artifacts. File system logs. File system log is a log that records disk I/O events or transactions that occur in the file system. There are two log files, $log file and $USNJRNL. The storage location is stored with the name $USNJRNL under the $extend folder in the same path as $log file under system drive. The advantage of this file system log is that it is possible to track the details of deleted files if it is possible to analyze detailed file system events that occurred during a certain period of time. Of course, it does not restore data from deleted files. $log file, called the NTFS transaction log file, is used to recover files that were in operation when a system error or sudden power loss occurred. It records all transaction and records unit. It also records all information before and after changes such as MFT record number, changed attributes, modified location, and value, so it can analyze the history of usage of file system relatively accurately. $log file has a default size of 64 megabytes. The size is usually enough to record for about 2 to 3 hours of content. It is an absurdly insufficient value to carry out an accident analysis. Therefore, you need to increase the size of $log file to a reasonable level. You can set the capacity of $log file with the command chkdisk. The following is a graphic representation of the approximate structure of $log file. The $data attribute of $log file is non-resident, and the area is divided into a restart area and a logging area. Each page consists of 4,096 bytes per page. Restart area points to the last working job record, the first two page areas of the file. The logging area is where the actual job records are recorded, starting immediately after the restart area and is divided into buffer page area and general page area. $USNJRNL is also a file change event management log file for use with a more stable file system. It is used to determine whether an application program has changed a specific file, and it is stored and managed in a sequential manner on a record basis. The record contains information about what happened to the file, so if you analyze it correctly, you can get powerful data flow information in combination with the information obtained through $log file. The $USNJRNL log file stores logs for 1 to 2 days when the computer is used for 24 hours, and logs about 4 to 5 days when it is used for about 8 hours. Like $log file, the $USNJRNL file can also be configured with the fsutil command. The $USNJRNL file consists of two files, $max and $j. The contents of the actual log can be found in $j. The following is an illustration of the internal structure of the $USNJRNL file and the internal structure of the $j file. You can see that $max and $j are composed of ADS. If we look at the structure of $j attribute, we can see that the logged records of variable size are listed consecutively, and that the beginning of attribute is comprised of sparse area filled with 0. The reason for this structure is that the operating system tries to keep the size of the log data stored in the $j attribute constant. $j attribute adds new log records to the end of the attribute. If the total size of the added records exceeds the allocation size, check that the total log data size exceeds the maximum size, including additional records. If the size of total log data exceeds the maximum size, fill the front part of log data with as many 0 per allocation size and make it into sparse area. Therefore, the logical size of the $j attribute continues to grow, but the area to which the actual data is allocated remains constant. If the malicious code is infected with the system in which the accident occurred, the file input/output event by the malicious code occurs. At this time, if the log capacity is insufficient or cannot respond quickly, the event related to malicious code cannot be confirmed. Therefore, it is necessary to increase the capacity in consideration of the lifetime of the log file or to prepare a quick response procedure. The following is a list of tools that can analyze file system log files. It can be downloaded free of charge through the URL. Volume Shadow Copy. The System Restore Point has been using Windows Volume Shadow Copy (VSC) instead of Restore Point since Windows Vista. The System Restore Point restores the system to a specific point in the past without backing up the operating system. It is activated by default when the operating system is installed. VSC can be used to recover deleted files, avoid file locking problems, and encrypt files. Recently, VSC has been the spotlight due to ransomware issue. The settings related to VSC can be checked in System Properties, Advanced System Settings, System Protection tab. By default, the system volume is VSC enabled, and the rest of the volume must be set by the user. VSC-related files are stored in the System Volume Information folder under System Drive. The file cannot be accessed or copied in live state, so you must use a specific tool or extract it directly from disk. When configuring VSC, the list of files to exclude from the copy can be set through the registry. The VSC can be set manually as above, but it is also automatically assigned when the service is running. Basically, it is stored per every 24 hours or per every 7 days. It also creates a VSC before Windows updates and sets backup points for system stability even when installing unsigned drivers. Finally, the VSC is created even if the program calls the API associated with the snapshot. VSC can be set on a per volume basis and can be restored on a per file or per folder basis. The following is the confirmation screen by setting the restore point to the folder. VSC-related settings are also available through the VSS-admin command. VSS-admin is a command line interface command, and you can check or change the settings for VSC with a simple option. The following figure shows the VSC configuration status of the C drive through the VSS-admin command. You can see that the original volume and the shadow copy volume are connected. The Windows system basically provides a command to mount the VSC via mklink command. You can mount the VSC file stored on disk to a specific path of the volume through the corresponding command. On the next screen, you can see that a folder named VSC1 and a specific VSC file are mounted under the C drive through mklink. VSC volumes connected to the system can be extracted in various ways. Among them, there is a method of imaging a volume using a specific tool. Typical tools for performing imaging are FTK Imager and DD. The figure shows VSC volume imaging using FTK and DD. There is a way to image the entire VSC volume, but there is also a way to copy all the files stored on the VSC volume using RoboCopy. RoboCopy supports robust file copying as a built-in command in Windows. The following is an example of using the RoboCopy command to copy files stored in the VSC volume, and an example of copying only certain types of files. The following is a tool named Shadow Explorer, a VSC-related tool that can be downloaded free of charge from the internet. It can be downloaded through the URL. As above, this is an example of VSC-related tools. Shadow Copy View is a VSC-related tool that can be downloaded free of charge from the internet. It can be downloaded through the URL. To analyze the VSC from the online system, first check the VSC information of the analyzed volume through the VSS admin command and connect the VSC to the specific folder through MK-Link. Of course, you can use tools such as Shadow Explorer or Shadow Copy View to link folders to the VSC for analysis. Data is collected through imaging or file copy to the connected VSC volume, and the collected data is analyzed. To analyze the VSC in the offline system, first mount the disk or image file to be analyzed on the analysis system. Then, the analysis is performed in the same manner as the analysis method of the online system described above for the connected disk. By comparing and analyzing the artifacts extracted from each VSC, events occurring in the system can be confirmed. The following is a screen to compare the external storage medium connection trace information extracted from VSC to confirm the difference. It can be seen that the external storage medium connection trace recorded in VSC3 is not confirmed in VSC2. Recently, attackers are trying very hard to hide their traces unlike the past. In many cases, the trail data is manipulated to confuse the forensic analysis, and the trace of all the system passed through is deleted except for the target system. For this reason, it is difficult to analyze the incident. Of course, if the accident response is fast, you can respond in a variety of ways, but in most cases, you will not know until after a considerable period of time after an accident has occurred. In addition, many traces of analysis are lost in the analysis process. In this situation, VSC helps to identify the cause of the violation. We hope that you become familiar with the VSC analysis process and use it in case of an accident.